Finalist 11, penultimate contestant for today from the Faculty of Engineering is Niraj Ramesh Dayama. His research interests include mathematical optimization, operations research and scheduling. For his PhD at Monash University, Niraj is hosted by CSIRO for research on numerical computing and mathematical modeling techniques. His title is Efficient Scheduling of Operations at Shipping Ports. Are you ready to go?
Eager.
Off you go.
Respected professors, fellow research workers, friends. I'm one of the lucky PhD students who get to select, define, and bring in their own PhD research topics. A few years ago, I was employed with a famous engineering consultancy organization. My team was involved in redesigning the daily operational schedule of a large shipping port in Europe. The shipping ports are interesting places. Every day, some 100 to 500 cargo containers will be brought in on ships, trains, or trucks. They will be sent out within, let's say, 8 to 10 days. Lots of different machines will be working simultaneously on many interrelated activities for these containers. Out of the total cost of international trade and commerce, some 15% is spent in these ports. That's a huge amount. My team managed to reduce it by about 1%. The employer was happy, the port was happy, everyone was happy. I was not happy. Because one fine day, a crane operator walked up to me with that day's schedule, made a few changes here and there, and managed to further improve the efficiency by another 3%. His human intuition and gut feeling was working way better than my computers. It was a humbling experience. I decided to do my PhD on finding the best operating schedule for ports, something that allows us to get our required products from food grains to iPods, cheaper, faster, and better. In my field of mathematical programming and operations research, such problems are termed as constrained optimization problems. The best and most established way of solving them exactly is, let's say, to model them on a three-dimensional system, where one axis talks about the activity to be done, second axis tells which machine is doing it, and third axis tells at what time is it done. The problem looks like an odd-shaped box, not this simple, and the solution is going to be in some corner of that box somewhere. Put aside the mathematics. Imagine that you have been given a big, nice, beautiful cake. In some corner of this cake, there's a diamond ring hidden. You want to quickly find that ring. What do? Take a knife and cut the cake. Look at the pieces. Do you see the ring? No. Keep cutting till you eventually get the ring. Easy to say, but if the cake is as big as this building and that knife is this small, then even the most advanced systems are going to take a long time in finding the solution. So people end up giving something approximate, something far from the best, and then some crane operator beats your solution. My approach, make the cutting process smarter. I first take a handful of robotic ants and put them on the cake, allow them to dig in. Now when I start cutting and judge the pieces, my ants sort of tell me that, hey, the solution is going to be in this bottom right corner over here. Within a very few, very smart cuts, I managed to get the solution. In effect, the problem that could not be solved earlier on supercomputers can now be solved on a laptop. I accept that my research is not something glamorous. I mean, I'm not doing rocket science. But then, I believe research is not about glamour. It is about a sustained endeavor to enrich lives. If this project is doing that, you are the best to decide. Thank you.